It's a week from Friday. Yeah. What? Okay, okay. Makes sense. All right, so I'm going to do number 9 from internal loads. Do you have a question? No. Thinking out loud. Okay, so internal loads, number 9. Um, okay, so this one has a pin joint in the middle. And a roller at the right end. And a torque over here of 4,000 Newton meters. Any idea how many Newton meters of torque you can apply with like a screwdriver? Is it 100 or 1,000 or 10 or 1? I think it's about 10 is about as much as you could probably do with a screwdriver. And then we have distributed load with the triangular shape, and maximum is 15,000 newtons per meter. Um, and this thing also has a weight of 800 newtons. Um, the whole thing is 1 meter, and the pin joint is at the middle, so it's half a meter each side. Um, all right, well, the first thing we have to do is calculate the external loads. So first I'm going to isolate the whole thing. And once you've chosen what to isolate, you can treat distributed loads as point forces. So we have a torque over here. We have a weight force acting at the middle of 800. We have an unknown vector at the pin joint. That's at the same place as that 800. I'll call that RP for pin. The triangular distributed load acts a third of the way from the roller toward the pin, and that's 3750. And then you have a force RR, the reaction at the roller, and the force of 10,000 newtons. Newton's second law says RP, break it up into components, plus 0, negative 800, plus 0, negative 3750, plus 0, positive RR, plus 10,000, 0, is equal to zeros. Okay, and then we have to do two. Oh, I'm missing one thing in the free body diagram. What's the thing that I'm missing? That's true, but that's not the thing I was thinking of. Yes, exactly. So since we're applying this couple of 4,000 Newton meters over here, if something wasn't counteracting that, this thing would just spin about the x-axis. The thing that would counteract that couple is the pin joint. The pin going through it or whatever it's rotating about keeps it from rotating. So we also have to put I guess I'll do it like this. I'll call that the torque pin, TP. The base of this triangle is 0.5. 0.5 times 15,000 is 7,500. And then the area of a triangle is 1/2 base times height. So half of 7,500 is 3,750, right? So now I'll do the moment equation about the x-axis. By the way, you could do this all as a single vector equation where you just have stuff going on in the x component and the z component. I'm used to breaking them up into two separate ones, but so we have in the x direction negative 4,000 plus torque at the pin is equal to 0. Okay, so what do we know so far? We know RPX is negative 10,000. From this one, we know the torque at the pin is positive 4,000. This is newtons. This one's Newton meters. And then the moment equation about the z-axis. Let's put the about point at the middle. So the 800 doesn't do anything. RP doesn't do anything. What's the moment arm for the 3750? 2/3 times 0.5. So that's just 0.3 repeating. So 0.3 repeating times 3750. And then, yeah, think about the direction. That would make it rotate clockwise around the pin, around the about point. So that's negative. And then you have RR, that is a moment arm of 0.5 times RR. And that would make it rotate counterclockwise, so this is positive. And so this tells us that RR is, I can't do that. What's 0.3 repeating times 3750 times 2? Ooh, 2,500 newtons. We have this, and then we also know the x component here. And now calculate RPY. $4,550 minus 2,500 is 2,050. Positive. Yeah, yeah, you can do that. You could do yes, you would have to do it as, so like if you're writing it out like this, yeah, I guess the way I would write that out in the moments is you'd have negative 4,000, 0, 0. You'd have the P 0, 0. You'd have the ones about the z-axis would be like 0, 0, 0.5 RR. And you'd want to write out the separate, do it as vectors, and then you just sum up those vectors and set them equal to 0. Yep. The pin. Yeah. But that from the pin to the end is only half a meter. So yes, you're right that it's 2/3 of this distance from here to here, but this distance is only a half. Yeah, sure. Okay, so now we can do the cuts. How many cuts are there going to be? So how many cuts? In order to do that, you have to think of all the loads on this thing before you treat the distributed loads as point forces. So what do we have going on? We have a torque over here. We have a bunch of stuff at the middle. We don't have the 800. That's sort of a key thing. So we have this force at the pin. We have the couple at the pin. We have this distributed load. We have the roller. Okay. And now we have the weight. And for the first part of the problem, we represented the weight. We represented the weight as a point force, but weight isn't really a point force. So before you represent distributed loads as point forces, the weight is this. Okay. And so now we're looking for places where, well, we know where the endpoints are two of these key points. And now we're looking for any place there's a point load, besides the endpoints, any place there's a point load, or any place a distributed load function changes. So all of these end up telling us this, except the key thing that I want you to notice here is when you look at the weight force as a distributed load, there's nothing that happens with the weight force at this midpoint, okay? And so if these other things weren't here, we wouldn't need to treat this as one of those key points that determine how many cuts to make, okay? Because it's just a uniform distributed load, the weight force, okay? You see what I'm getting at? If you look at the free body, that first free body diagram I drew, we treat the weight force like it's acting at this pin here. You would think that something important with the weight force happens at the midpoint, but it doesn't, okay? So if you're if all this has is like a cantilever and its weight, you don't want to think of it, you don't want to do two separate cuts and think of the weight as acting at the midpoint. You just want to do one cut because the weight is a single distributed load that and the function never changes. Okay, so there's three of these points. That means we're going to have two cuts. So cut 1 represents x values between 0 and 0.5. And it has the weight, the torque, and that's all. Then the internal loads. Bless you. Okay, so we have the torque over here of 4,000. We have the weight force. And what's the magnitude of that uniform distributed load? How do we calculate that for the weight force? We have a total weight of 800 newtons. We have a total length of 1. So the newtons per meter is 800 divided by 1. So 800 newtons per meter. And then we have these internal loads, T, V, M, and torque. Before I do Newton's second law, we have to present that weight now as a distributed load, as a point force. It is a distributed load. So we still have this, 4,000. We still have the internal loads. And as a point force, what's that distributed load? So this distance is x. So what's it going to be? 800x, and where does it act? Yep, at the middle. Newton's second law says 0, negative 800x plus t negative v is equal to zeros. So t is equal to 0, v is equal to negative 800x. And then the moment equation about the x-axis, we have negative 4,000. The only other couple about the x-axis is fancy t. And so the internal torque is equal to positive 4,000. And then the moment equation about the z-axis, I always use the left end as the about point. So we have the force of 800x. What's its moment arm? X over 2, yep. So x over 2 times 800x. And is that clockwise or counterclockwise? Around the about point. Clockwise, so that's negative. And then we have plus m minus vx is equal to 0. So m is equal to 400x squared plus bx. And so m is equal to 400x squared minus 800x squared. And so m is equal to negative 400x squared. And now you can check all the derivatives and make sure they work out. dm dx is equal to v. Negative dv dx is equal to 800. And that's the downward distributed load function. Any questions about the first cut? Yep. Mm-hmm. The cuts, every cut represents, like an infinite number of actual cuts, you know what I mean? And so, right, the function representing the weight, you're right, will never change. That's right. All right, so now cut 2 represents x values between 0.5 and 1. And this time, all right, we still have the 4,000 over here. We still have the distributed load representing the weight, and that has a magnitude of 800. We still have the stuff happening at the pin, so that's a force vector of, we got that in the first, when we isolated the whole thing. So RP is negative 1,000, 2050. And then we also have the torque that's equal to 4,000. And then we have the triangular distributed load. And that does not have a maximum value of 15,000 because we're not going all the way to the end. So we have to figure out the function of that line in terms of x. Okay, so we know this is going to be mx plus b. So y is equal to mx plus b. For m, we can just take the rise over run. So it rises from 0 to 15,000 over a run of 0.5. So that's 30,000. Now to find b, we know that when x is equal to when x is equal to 0.5, y is equal to 0. So 0 is equal to 30,000 times 0.5 plus b, so b is equal to negative 30,000. And so the function, what? Yeah. And so that function is 30,000 x minus 15,000. And then you have the distributed load, the internal loads. And now we have to represent these as point forces, the two distributed loads. The weight is easy. The triangular distributed load has a height of 30,000 x minus 15,000. And what's its base? The width of it is x minus 0.5. Because we're just talking about this distance from here. Okay. Right. Okay, we're on the second side. So that triangular distributed load starts at an x value of 0.5 and ends at x. So this distance is just x minus 0.5. And so the area is x minus 5 times, this is also x minus 0.5, and then multiply the whole thing by 30,000. So that's x squared minus x plus 0.25 times 30,000. So 30,000 x squared minus 30,000 x plus 7,500. What? Yep. Okay, so now I'll redraw this free body diagram. We have a torque of 4,000. At the middle, we have a force of negative 1,000, positive 2050. And we also have a torque of positive 4,000. I don't know. 10,000? Yep, thanks. Negative 10,000. And then we have a weight of 800x. And then we have the force from the triangular distributed load. It's a downward force of 15,000 x squared minus 15,000x plus 3750. And then the internal loads. And our about point will be this. So Newton's second law says 0, negative 800x plus negative 10,000, 2050 plus, now this force has a magnitude of 15,000 x squared minus 15,000 x blah, 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 but that's in the negative y direction. So this is 0, and then all these negative. Again, I think the best way to think of that is this is the magnitude, and we're multiplying it by a unit vector 0, negative 1. So 0 for x, and then negative 15,000 x squared plus 15,000 x minus 3750. And then plus t negative v. So t on the second half is equal to 10,000. So is the second half stretching or being compressed? Yep. A positive value of T is tension. And then shear force is negative 15,000 x squared plus 7,000 x when you, oh no, that's 800. So plus 14,200x, the 15,000x minus 800x. And then minus 1,700. You can do the derivative check right now, and what it has to give you is negative dv dx has to come out to be the downward facing distributed load, the total downward facing distributed load. So positive 30,000x plus 14,200 has to be what you get if you add up this function, this function. $1,700. Oh, so if you add up, okay, so if you add up this plus this, you get 30,000x minus 1,400. So that does come out, right? Right? And now the moments are going to get super messy. Um, well, the X one won't be bad. So we're just adding up negative 4,000 plus 4,000 plus t is equal to 0. So the internal torque on the second half is just equal to 0. But about the z-axis, so we have 800x with a moment arm of x over 2. Yes. Yes. Okay. So, no, this is of everything in internal loads, this is the thing people get confused about the most. And even people who had it straight a week ago get confused about it a week later. So I said this before, but this won't be the last time. So we are not cutting a piece that starts, like this doesn't represent what our free body diagram is of. This represents the range of possible right hands of our cut. But we always start all the way at the left of our cut. So our piece goes from the far left end up to some X value that's in this range. Okay, so we always include everything all the way at the left. And this just tells us where we stop. What? So let me talk about that in a second. Let's finish doing this and then I'll talk about that. Basically, the answer is if a problem is a lot easier to do a mirror image of, like you're looking at this beam and you're like, God, I wish everything was backwards. It would be so easy to calculate. Just go over here and look at the beam and do that problem. Yeah. Will it ever be that there's like a pin that doesn't cancel the torque entirely? You have two things that have to balance one? It will never, no, because it wouldn't be statically determinate. So not in this section, but when we get into statically indeterminate structures, then yes. Okay, so the about point is the red dot. So first we have the downward force of 800x with a moment arm of x over 2. So x over 2 times 800x. And that's a clockwise moment, so negative. And then we have the y component of the pin force. So we have the force of 2050 with a moment arm of 0.5, and that's counterclockwise. So plus 0.5 times 2050. And then we have the messy function. Okay, so magnitude of that force is this quadratic function. So 15,000 x squared minus 15,000 x plus 3750. Is that what it was? And now what's its moment arm? Well, we know it's 2/3 of the way from here to here plus 0.5. Okay, so this distance is x minus 0.5. This distance is 2/3 of that. and then we're going to add on 0.5. Are you with me on that? Um, so the moment arm, this a little. Okay, so the moment arm is 0.5. I'll make this brackets plus 2/3 of x minus 0.5. And that's a downward force that would make a clockwise rotation. So this is negative. And then plus m minus vx is equal to 0. Yep. Because this this does not have a length of 1. Okay, it has a length of x. We don't know what that x is, you know, and so like x could be anything from 0.50001 to 0.99999. If the length was 0.50001, then the length of that triangular distributed load would just be 0.00001. If the length is 0.999, then the length of that triangular distributed load is 0.4999, you know? So that moment arm has to be true for any value of x between 0.5 and 1. I think maybe this is where we stop on this problem, but you know, I don't want to take the fun out of this for you. But we didn't get, yeah, right. So, right, you're going to have to multiply this by x and blah, blah, blah. But, um, so, okay, so yeah, I'm going to stop there, but that's procedure. Anybody have any questions about that? Yeah. Okay.
I just want to know but you take 3x minus x minus 5 over the distance
For the moment arm?
from the other side.
Yeah, good way to do it. That makes more sense, actually. So go, instead of thinking of it as 0.5 plus 2/3 of this thing, just think of it as x minus 1/3 of, it's not really any, I mean, obviously they come out to be the same if you do the algebra. But just think of going all the way to the end of x and then backtracking instead of going, I don't know, do whatever makes sense to you. I think actually, now that I think about it, 50% of the time I do one and 50% of the time I do the other. Okay, the next thing I want to do, I'm not going to do it today. We need to get done with internal loads, but there's one more thing I want to do. What if you had a problem like this? That doesn't look too bad, right? Um, The one we just did looks a lot worse than that. This is surprisingly ugly, though, to calculate because when you do the cut, the fact that that triangular distributed load is facing the direction it is means that your cut removes its triangular character. You know what I mean? Like we do this cut, and now we have this trapezoidal distributed load. That is what I would do, except here's the only downside. We are going to do some problems where you just have to do them like this because what if you had something like this? Now you're stuck. Yeah, right. Yeah, that would be a pain, um, but then anyways, you have to do one of the backwards ones no matter which side you're on. But yeah, I really like that the get up and walk approach to complicated problems. Just um, all you're trying to do is come up with a relationship between the internal loads in some place in the um, and like a material point in the beam. So there's no reason not to. So for this one, yeah, this top one, uh, the way to do that is just think of it as in the opposite direction. Oh yeah, it is kind of like that. Yeah. So what we're going to do is break it up into. So we'll break it up into triangle sitting on top of a rectangle. This digitizer is getting funky. That's why it looks like I'm like developing Parkinson's or whatever. But and so then we'll just think of this as the sum of two different distributed loads. You don't even have to add them together. You have a you're going to have a point force that's equal to the area of that rectangle acting there, and a point force equal to the area of that triangle acting a third away, and do it like that. So remember, no school tomorrow. Um, there for sure is software that does this, and I don't really have any